shape of a cone is manufactured with the radius and height to be 3 and 7 inches, respectively. If the errors in the radius and the height are the same, what can the maximum error be so that the relative percent error of the volume is no more than 3.2%? So I see a 0.04 inches. Oh, so sorry. And another 0.04. Okay. And so I see a lot of estimated propagated errors of 2.111s and a 0.04. Looks like a lot of us. Oh, wait, this one's different. This one's a 0.002. Okay, so we'll take a close look. That one's a 0.04. That one's a 0.04. That one I have no idea what that is. It's something that is unsimplified that I'm not going to simplify. Okay. Do you think it's 0.04? Alright. So volume of a cone is 1/3 pi r squared h, right? So I'm gonna, like, when we're done with the lesson today, we're gonna do a related rates cone problem. So it'll be fun. It'll be really fun. Okay. All right. So I got a projected volume of 21 pi. So that would be ideal if which is what you guys got that. If there wasn't an error. Okay. So delta R and delta H are the same. I use delta R for both, which, look at that, like great minds. This is great. We all look at us all like doing the same thing. All right. Oh, okay. You guys did delta H and just stuck stuff in. That's fine. Okay. All right. So there's my dV. So my dV is my partial V partial R. So partial with respect to R times delta R plus partial with respect to H times, again, it'd be delta H, but delta H and delta R are the same. So times another delta R, right? All right, so plugging in the amounts that we know, we get a dV of 17 pi times some unknown error amount, right? We want this divided by 21 pi to be no more than 3.2%. So it's just a little, you set this up and do a little equation. So do this times 21 pi divided by 17 pi, and I got around 0.04. Look at that. So we all know. So well done to those of you who got 0.04. Yes, Lily.
Okay, so I don't know if this is like nitpicky or not, but in this problem you use delta R, and I noticed we've been using like
DR, yeah.
I mean, I just like didn't know if they're like interchangeable.
For all of these, well, your change in your input should be exact. So delta R and dr for your input should be the same, because it's easier for me to show in 2 dimensions. So I'm not going to do the whole 3-dimensional thing, but if you have it in 2 dimensions, so if we have a function and so we've got this and we've got this, and this is our delta x, right? So, oh, this is a terrible picture. It's going to be really steep. Okay, this right here, I don't know why I drew that secant line. This would be our delta y, right? This is our change in x. When our x changes by this amount, our y changes by this amount, right? When we approximate it using a tangent line, so we're using the derivative, that's our dy is the approximate change in y, but the change in x is still the same, right? So your delta x and your dx should be the same, but your delta y, your output change, should be different. That's why it's an approximation for the change in your output, but it's not an approximation for the change in the input. The input, we use delta x and dx kind of interchangeably. So that's a fair question. Yes?
Also, could dy also be an underestimation of delta y?
Yes, it could.
So
Yeah.
Kind of smaller.
And how would it end up being an underestimation? If your function was concave up, right? Yes.
Oh yeah, I remember that now.
Right? Okay. So today we're doing chain rule. This is section 14.5. I can apply the chain rule to functions of several variables, and I can find partial derivatives implicitly. We're going to add on here, I can solve related rates problems using the new chain rule that I just learned. I want to do it just for fun.
You're the only one who thinks that's fun.
Yo, chill. I'm not a massive kid.
Did I ever teach you we never have enough time when we do related rates, but when we did related rates last year, did I mention at least that there were multiple methods for doing related rates problems? Did I mention? Do you guys remember? I mean, I know, honestly, I can't even remember what I said this morning, so there's no way if I was a student that I would remember some random thing that my teacher said a year ago, right?
But the thing you showed us was multiplying
The differentials. Okay, that's what we're doing today, right? So we're going to learn the math behind multiplying the differentials today. So we're learning the alternate method for doing related rates problems. And I should have put at least one related rates problem in your homework, but I didn't. But there are some in your book that I could do if I wanted to. I thought about it, and the reason I know is because I was looking at your test for this unit, and I looked at the chain rule, and the chain rule question I had on your test was way too easy. And the reason it was way too easy, honestly, was because last year I didn't have a good solid grasp on chain rule. So I put an easy problem on there because I didn't do it service. But I really, really am liking chain rule now a lot, and so I put a better problem on there. And so I was going through all these different chain rule problems, and then I came across all these related rates questions that you can use chain rule on, and I'm like, ooh, I could put a related rates question on there. But I didn't. But I could, right? The test is still in writing mode, so yeah. Okay. So anyway, we're going to do a quick second warm-up. You can just do this on paper. Any method you want, so you don't have to know chain rule to do this. So suppose W equals x squared y minus y squared, where x equals sine t and y equals e to the t. Find dw dt when t equals 0. Any method you want. So take a minute, work on it quietly and independently, then feel free to discuss with your group members. So Michelle, tell me what you did.
So right away I substituted x and y, like the values, into the w equation.
I think that's what most people did. Is that what most people did?
Yeah.
Substituted in and then found the derivative. What rule did you have to use? And
what's it called? Product rule.
product rule. Very good. Okay. All right. So yeah. So the first method is to just substitute. Replace the x with sine t. Replace the y with e to the t, and then you just find the derivative dw dt. I asked for it at t equals 0, so you plug in your 0. Oh, where's my answer? I never plugged in my 0. Did I ever find an answer? Nope, my answers are incomplete. So let's just pretend that we're gonna add this on here. dw dt at t equals 0 equals, well, this whole thing right here is 0, right? Plus 0, so it's just negative 2 e to the 0 or negative 2. Okay. All right. The second method is a chain rule method, which I think is what some of you were kind of starting to think about using a little bit, right? Because it should look, if it didn't have this, it should look just like what you've been doing for the last couple days, which is finding a total differential, right? Okay, so partial x times dx, partial y times dy, partial z, there's another, partial y, the dy was just in two parts. So anyway, partial x times dx plus partial y times dy. So you end up with the same thing. But anyway, that's gonna be what we're getting into today. All right, so this is, you don't have to write this whole page down. I'll show you what to write at the end. This is me kind of just leading you into chain rule. Last year, when we talked about chain rule, we used to say the derivative of f of g of x is f prime of g of x times g prime of x. So that's what you thought of when you thought of chain rule. But there's an alternate way to write chain rule. See you tomorrow. Which is dy dt equals dy dx times dx dt. So it's kind of like you have a function inside of a function. So here, it's kind of like you have a function embedded inside of another function, right? So here you have another function kind of embedded inside of another function. So another way to write it, and this is just a simple single variable version, is dy dt equals dy dx times dx dt, where dy dx is like your outer derivative, the derivative, say you have like y with respect to x, and then your inside function, which is your x with respect to t, right? And so you do dy dx, outer derivative, times dx dt, inner derivative. So what you end up with, and you kind of think about it like the dx's kind of cancel. This is what I was kind of talking about when I was leading you into related rates using an alternate method. So anyway, so this and this are actually equivalent. They're just kind of written in a different way. So, all right. So last week, then we're going to put it all together. So last week we learned how to find a total differential. So dz equals partial x dx plus partial y dy. If we take this and put it together, this is what we come up with, this chain rule. There's actually a big, long, giant derivation and proof in your book, which I am not going to get into. But anyway, so mine is just a very simplistic way of explaining it, but I think it makes sense. So your dz dt equals partial z partial x times dx dt plus partial z partial y times dy dt. And if you had, like, say you had z, like, say z was in terms of, w and x and y, or, t and u and v and w and x and y, that's okay. It's just each partial derivative times that derivative's differential with respect to whatever the input variable is. So the key here is that all your input functions are in terms of the same input variable. Now, in a few minutes, we're going to learn another chain rule where all your input functions can also have multiple input variables. So we could do chain rules of multiple variables of multiple functions with multiple variables, right? And we could just have this whole big giant, like, massive tree of chains, right? It's so cool once you get into it. But we're just going to start simple, where your input functions are both in terms of the same variable, and then your multivariable function is in terms of those input functions. All right, so I was kind of trying to wrap my head around how this worked, and so I tried to explain it. This is what I came up with. Okay, so x and y, if those are both defined, say, in terms of t or theta or whatever input variable we picked, right? That means that x and y, you could really think of those as a set of parametric equations, right? So what does the graph of a set of parametric equations look like? It just looks like a curve, right? So what we end up with for our input is we get the set of all x's and y's that are on some parametrically defined curve. Whatever that curve might be. Might be a circle, might be a squiggle, could be a figure eight, could be whatever. So our inputs for z end up being restricted to just the x's and y's, the ordered pairs that are on whatever curve we're talking about, right? So whatever our curve is, if we have some, you know what we could do? We could do, I put this too low now. Let's just pretend it's a cardioid, right? Okay, so we have some parametrically defined curve, and then, so the points, our input for our z would only be the points along this curve. And then if we're finding dz dt, what we're really doing is finding the rate of change of z as we move along the curve. So because t, remember, as you increase your values of t, right, you draw your curve, right? So as your t changes, you're moving along the curve. So the question is, how is your output, your ultimate output function, your z, whatever it represents, how is z changing as t changes, right? So t creates this graph, and then z is some function based on the points on this graph, and then how does z change as t changes, so as you move along the curve. So anyway, so that was my little mini interpretation there of what's going on. Okay, so the first problem we're going to do with our new big chain rule is an application problem. The pressure P, Tejesh, you with me?
Yeah, sorry.
That's okay.
I was just thinking.
I could see that. Okay. All right. The pressure P in kilopascals, volume V in liters, and temperature big T in kelvins of a mole of an ideal gas. When I lived in Georgia, we used to get moles all the time in our yard. And do they have moles up in the north?
Yeah.
Do they really?
In my yard.
Oh yeah?
In the backyard.
Really bad? I've never seen a mole since I moved to
They burrow
Minnesota.
like under
Yeah.
ground and it destroys the grass.
And it destroys everything, yeah.
Yeah.
But they're so cute. I mean, when they poke their little heads, they're so
Oh my gosh.
cute.
What? Wait, really?
Yeah, you don't think moles are cute?
I think I look really.
They're so weird looking with the little.
It's like
Aren't they like the
this
same?
star.
Yeah, they have the stuff coming out of their nose, like.
It's like a star nose.
Okay. So anyway, but we're not talking about those kind of moles. So we're talking about moles of an ideal gas. All right. So the pressure, volume, and temperature are related by the equation PV equals 8.31 T. Find the rate at which the pressure is changing when the temperature is 300 Kelvin and is increasing at a rate of 0.1 kelvins per second, and the volume is 100 liters and is increasing at a rate of 0.2 liters per second. Total related rates question. You could absolutely do this with related rates without ever having walked into Calc 3, right? You could do some implicit differentiation with a little bit of product rule mixed in, right? So you'd have your dP dt times V plus P times dV dt equals 8.31 dt dt, plug in all your numbers and solve, right? You could do that. We are going to do this using differentials. So since we're looking for, what are we looking for? We're looking for the rate at which the pressure is changing. So we're looking for dP d little t, not big T. That's what we're looking for, right? Okay. Solve your equation for the variable you're looking for the rate for. So solve it for P. So we have P equals 8.31 big T over V. I'm going to write out chain rule real quick just so that we are all kind of on the same page, right? So dP dt equals partial T, partial P, partial, oh, I'm already off to the bad start. Here we go. Let's do this right. Partial P, partial T, dt dt plus partial P, partial V times dV right? It's just all the partials of all your input variables times their derivatives of their, with respect to their input variables, right? I'm going to let you work. I'm going to write some things that we're given. Let's see. We're told t equals 300. We're told dt equals 0.1. We're told v equals 100. And we're told dv dt equals 0.2.
And times 0.1. Times 0.1. And then plus. So negative. What's dt? So that's negative 8.31 t over v squared times 0.2. And then
Never pause. All right, so d dt equals, so partial p partial t, so that would be 8.31 over v, right? Times dt dt times dt plus partial b p partial v, so that would be negative 8.31 t over v squared times dv dt. Is that what you guys got for your derivative? Yeah. Okay. So then you're just plugging in all your numbers. So let's see. Remember my glasses. Okay, so 8.31 divided by 100. 8 times, what's dt dt? 0.1? Okay, so I get 0.00831 minus, and then I have 8.31 times 100 times, oh, I erased my dt, 0.2 divided by, so just, you know, I accidentally, when I was erasing some other stuff, I accidentally erased. Okay, so I got minus 0.04986. So this minus this. So I got negative 0.04155. Does that match what other people got?
Yeah.
Okay. All right. Units. Units for P over units for T. Kilopascals per second. I don't know how to abbreviate. How do you abbreviate pascals? kPa per second. There we go. I'm kind of curious if I should, I'm trying to decide if I should make you guys do this the old way just to see. No? Okay. All right. What if your input functions one variable. Okay, so suppose that z is some function in terms of x and y, but x is some function in terms of s and t, and y is some function in terms of s and t. Then you're going to have partials for your rates for z. So you're going to have a partial z partial s and a partial z partial t. You're going to have a rate of z with respect to s, and you're going to have a rate of z with respect to t. So you do each one separately, and then it's still this. So then you just kind of do, so it's partial with partial x times dx ds plus partial y dy ds. Again, these have to be partials too because there's multiple variables inside of the variables. So it's all partials. Once you get into multiples of multiples, it's all partials. And you can expand to more than 2 variables, which we're going to do in the next problem. You hate writing the dells? When I write them, when I write a normal D, I start with my top bar and go like that. But when I write a del, I start with the curly Q and go up like that. And it works well for me. So. So, yeah, except you don't have z in terms of s, so that's kind of the whole point. Yeah, Sophie.
So you would get like 2 different derivatives?
Yeah, you're going to get 2 different rates. A rate with respect to each different input variable for your inputs.
So there's no way to have a rate like...
One big rate? Well, when we get to Friday, we're going to put it all together.
Okay.
Alright. Still see you right. Ian, how you doing? Good. I'm doing all right. Yeah, having a fairly good day. Yeah. So, I'm not available after school today. We have a department league meeting. So, I don't know what we're talking about. We'll find out. Okay, moving on. All right, so this first one actually is an example I used last year that's pretty straightforward. Then the next one is extra fun. So we're going to find the rate of change of W with respect to S and the rate of change of W with respect to T if W equals 2xy, X equals S squared plus T squared, and Y equals S over T. So I have you do using both methods, but I do want you to learn how to do it just using chain rule because the deeper we go into the material, the more chain rule is actually going to poke his head back out, much like a mole in the ground, right? So anyway, yeah. So I'm going to have you, last year, I did everything, like I didn't see the point of chain rule and I was doing everything with substitution. And then all of a sudden I came like to a lesson where the only way to do it, this new concept we had to learn was with chain rule. And then I'm like, oh, I guess I do have to learn chain rule. So, which makes sense because, you know, they're not going to teach you something that you don't need. So, anyway, okay, but you can do it both ways. Or you can just do chain rule. The most important part that I want you to make sure that you can do is chain rule. So take a few minutes, chew on this one.
You mean
So, first thing, if we were to do it by substitution, which is not that important, but all you do is replace your x in your equation with what it is, replace your y with what it is, clean it up, and then just do your partials, right? So you do your partial s, and you do your partial t,
I don't know. That was hard in June.
and then you've got it, right? So,
It's got bullshit. It's
okay.
bullshit a little bit.
Okay. The second way is to do chain rule. And when you're doing chain rule, there was some confusion on how to start, right? So you look at your main function and you look at what you're trying to find. Let's just focus on the partial w, partial x. So we want partial w, partial s, partial w, partial s, without knowing anything else. You just look at your w and you see what variables it's in terms of. However many variables it's got in here, that's how many terms you're going to have in your expression, right? So we have two variables. We're going to need a term for our x, and we're going to need a term for our y. So we're going to have partial w, partial x, times partial x, partial whatever the letter is down here, plus partial w, partial y, times partial y, whatever the letter is down there. Right? So there, that would be the chain rule expression to find partial w, partial x. And then you do the same thing with t's. Right? So our answer. Okay. So there's my s, which just kind of plugging in. Now I think in order to make a match, I replaced my x's and y's with s's and t's just to make sure that I got the same thing. Did you guys leave them with x's and s's and t's?
Yeah.
Okay. I gotta check WebAssign to see if they're okay with that or if they want it all down to this, the s's and t's. I'll have to check and see. We can check that before we leave today. All right, and then the same thing with your y's. Or with your t's. So, anyway. Okay. This next one, if you can do this, you've got it. Okay? And it's not that big. It's not a huge problem. Okay. I could have asked for more. I didn't ask for that much. If u equals x to the fourth y plus y squared z cubed, where x equals rs e to the t, y equals rs squared e to the negative t, and z equals r squared s sine t, find the value of partial u partial s when r is 2, s is 1, and t is 0. So you have 3 input variables for your main function, and then each input variable has 3 input variables.
This is so mean, Miss Trent.
It's really not as bad as you think. Yeah, same thing, kind of extended. Okay, I'm repausing. All right, so I personally like to kind of write out my generic formula first, so I kind of know what I need to go for. So, is that okay?
Yeah.
Nathan?
Oh yeah.
That's okay? Okay. So remember, I want partial u, partial s. I look at my u, and so for each variable that you have, you're going to have a term in here, right? Okay, if you have 4 variables, you're going to have 4 terms, right? All right. So partial u, partial x, partial s, and then the same thing with the y, and the same thing with the z. All right, then it's just a matter of crunching all the math out, finding all your partials, right? So those were all my partials. And then I went ahead and found my x, my y, and my z at r equals 2, s equals 1, t equals 0, because no one wants to sit there and like re-plug those numbers in every time for all this stuff, right? So, right, yeah. So anyway, so I went ahead and found them first, and then just plugged in I had 6 numbers to plug in. So X, Y, Z, R, S, T. And when all was said and done, I got 192. So are there any questions? Any questions on this? Yes. 100%. This will be on the test. Yes. Who knows? Maybe 5.
Maybe it's one variable.
All right. Okay. So
Exactly.
what I'd like to do now, I'm going to close the video. Goodbye, video.